Okay, we're going to move on to question 67. This one is not for the faint of heart. So if you haven't done a lot of practice, you might want to hold off and try this one when you are feeling like you've mastered this material. So in this question, this is just kind of a more advanced example of a hot-cold type question in calorimetry. So we have this wafer of pure gold, 31.1 grams, and it's initially at 69.3 degrees, and we're going to drop it into a known mass of water, which is cooler. So the water is going to get warmer, and the gold's going to get cooler, and they're going to arrive at the same temperature. So I've written up here some of the numbers from the question. So we know the mass of the gold and the mass of the water. We know the initial temperature of the gold and the initial temperature of the water. So we expect that our final temperature will be somewhere in the middle. And then the final temperature is going to be the same number for both of these because they're going to reach thermal equilibrium with each other. So I'm just going to have one TF because the TF is going to apply to both substances, both the gold and the water. Okay, so as with all calorimetry problems, we start with setting Q equal to Q. Heat is leaving something and is going into something else. So in this case, the heat leaves the gold, so it's got a negative sign, and it goes into the water. So we can expand this into our equation that includes the mass of the gold, delta T for the gold, the heat capacity of the gold, the mass of the water, the change in temperature of the water, and the heat capacity of the water. Now let's think what we know. We know the masses, we know the heat capacities, and we know the initial temperature in each of these delta T's, but we don't know the final. So that's going to make our algebra pretty tricky. Okay, so let's just go ahead and plug in. So we're going to say okay, so on the negative side, we're going to have the mass of the gold times, I'm going to go ahead and put the heat capacity of the gold here, and this is something that you have to look up in order to do the question. Of course, you'll be given this on a quiz or an exam. And then delta T is final minus initial. So that is our negative Q term, and this all refers to the gold. Okay, then we're going to set that equal to our positive Q, which involves the water. So we're going to have the mass of the water times the heat capacity of water times T final minus the initial temperature of the water. So everything over here on this side is the water. So that in and of itself really isn't very tricky. It's just solving for the final temperature, which is a little tricky algebraically. Okay, so we're going to take and multiply these. So I'm going to have negative 3.98 joules per Kelvin, and then I'm going to multiply that times TF minus 69.3, and that's going to equal, I'm going to go ahead and combine these. That's going to give me 268 joules per, you know what, I should just have degrees Celsius everywhere in this problem because those are the numbers we were originally given. So sorry about that. I'm just going to include degrees Celsius everywhere. Okay, and then that gets multiplied by TF minus 27.8 degrees Celsius. All right, then I'm going to distribute these, and that gives me negative 3.98 joules per degree times TF plus 276 joules equals 268 joules per degree times TF minus 7.46 times 10 to the third joules. All right, so now I'm going to combine my joules, and then these terms can be combined. And what I end up with is 7740 joules. I move the joules over to the left. And then that equals 268 joules per degree times TF plus 3.98 joules per degree times TF. All right. Almost done. Okay, so now we're trying to solve for TF. So we have 7740 joules equals TF times 272 joules per degree. So I'm going to move this over here and divide, and I'm going to end up with degrees. So TF equals, T final equals 28.4 degrees Celsius. Okay, if we go back to our original information, we see that we are expecting some number between 27.8 and 69.3. So the answer we have, 28.4, is in between. Note that it's closer to the water because the water has a much higher heat capacity.